Hey guys, in this video, you will be learning about implicit differentiation. So by the end of the video, you will be able to use implicit differentiation to find the derivative of an equation, or, well, that should say and find the tangent line of an equation at a particular point. So just to give you guys a heads up, I'm making this video late at night, so if I mess up, reading some of the things here, just forgive me. It is pretty late. So I'm going to go ahead and begin with the introduction. Until this lesson, the functions that have been studied have all been in written form, written in the explicit form. Okay, where the variable y is explicitly written as a function of x. So these are examples of explicit forms of functions of x. So we have y is explicitly equal to x squared minus 5x plus 7. This is called explicit form because y is equal to a function of x. Okay, I could even say that 7 has an x, but raised to the 0 power, which really just cancels to 1. So all of these terms for y are all x terms. And the one below is f of x, which means function of x. And those are also in terms of x. And this is called explicit form. Some functions are only implied by an equation. For example, y is equal to 1 over x. I'm going to write it over here. Now ask yourself, is that an explicit form or is that an implicit form? Well, this is explicit because we have y explicitly equal to 1 over x. Now, y can be converted to implicit by doing just a simple algebraic technique, multiplying both sides by the reciprocal of 1 over x, which would just give you x times y is equal to 1. So y equals 1 over x is defined implicitly by the equation xy equals 1. So here are some examples of implicit form, implicitly defined functions, and note these are not always functions. In calculus, we tend to call these types of relations curves because they may not pass the vertical line test. And it'd be very hard to solve for y. It'd be very hard to convert this equation into explicit form because you have more than one y, and then both y's are being raised by a third and a square. So instead of solving for y and differentiating in terms of x, we're going to go ahead and use implicit differentiation. We're going to take the derivative of each term, even though they're not x terms. And I'll show you how to do that in the example below here. Okay, so these are examples of implicit, where y is supposed to be y is supposed to be some equation that involves x's. Okay, we're implicitly defining y to have some sort of relation with x. Okay, we don't know what it is because we can't solve it. But we're going to go ahead and take the derivative of these kinds of relations now, these curves. To understand how to find dy dx implicitly, we must realize that the differentiation is taking place with respect to x. How do I know that? How do I know that I'm taking a derivative with respect to x? The bottom part of this notation for derivative tells you that dx, you're taking the derivative with respect to x. So if I'm taking a derivative of some relation y or some function y, the bottom part is telling me take the derivative with respect to x. Okay? This means that when you differentiate in terms involving x alone, you can differentiate as usual. Just like the way you guys have been doing it. Power rule, chain rule, quotient, product rule. However, when you differentiate involving y, you must apply the chain rule. because you're assuming that y is defined implicitly, just like I stated above, implicitly, as a differentiable function of x. And this function, I just mentioned that this is not always going to be a function. Okay, it could be a non-function, like a curve. So just be very careful about saying function for the following, examples here below. So let's go ahead and begin with our first example. Let me just show you how to differentiate with respect to x. So differentiating with respect to x, let's go ahead and begin with the first example. How do I know that I'm differentiating with respect to x? This variable at the bottom is matching with the variable inside that I'm taking the derivative of here. So do they match? And the answer is yes. So what do? So differentiate as normal. Or I should say differentiate normally. So let's take the derivative. We know that this requires power rule, so you drop the 3, you keep the x, and you reduce the power by 1, and it's 3x squared. Now, just to let you guys know that chain rule is always part of your derivative process. I could even take the derivative of x and multiply it to the outside and write it as 3x squared times 1, which is the same thing as just 3x squared. Okay, and there's a special reason why I'm doing this, even though I don't need to, because I'm going to show you in the next example. We have that we're differentiating with respect to x. That's telling me differentiate this expression with respect to x. However, do they match? The answer is no. So use chain rule. Okay, now let me show you what that means using chain rule. Okay, so let's just take the derivative, like let's pretend that y is x. Drop the 3, keep the y, make the cube into a square, and then take the derivative of y and multiply it to the outside. That's chain rule, right? Like the way we did it here. We took the derivative of x. I took the derivative of x with respect to x, and that became 1. So what is the derivative of y with respect to x? Well, that is simply just, that is simply just dy dx. Or you can say y prime, since dy dx and y prime mean the same thing. They both mean derivative of y with respect to x, except for this notation, it's not explicitly stated with respect to x. Okay, so keep in mind that this is not a power to the 1, power of 1. It's a prime. Okay, so don't get these confused. I tell my students stick with this notation because you can literally see dy dx. Let's go ahead and do the next one. So I'm differentiating with respect to x. So that means that this term would be just normal differentiation. However, this term would be the chain rule differentiation. Okay, so let's go ahead and take the derivative of each term. So the derivative of x plus the derivative of 3y. This is a rule that you guys learned. It's a theorem. The derivative of two or more functions is just the sum or difference of the derivatives. So the derivative of x is 1 plus the derivative of 3y. Well, treat 3y like it was 3x. The derivative of 3y is just 3, but take the derivative of y and multiply it to the outside. So I'm going to pretend that y became 1. Now the derivative of y multiplied to the outside, dy dx. Cleaning this up, 1 plus 3 times dy dx. Okay, I want to just stop and make a note real quick in case maybe this example didn't make so much sense like the previous example. I want to just refresh about like our basic derivatives. For example, if I give you a function 6x to the fourth, and I asked you find the derivative of this function here. Well, you guys, without even thinking, involuntarily would just write y prime is equal to 24x cubed. Well, you've been doing implicit differentiation since pretty much the day one that we started talking about derivatives. The derivative of y becomes y prime, or in this notation, it's dy dx, and those two are the same. So it's no coincidence that the derivative of y just turns into dy dx. However, if it's a derivative of y cubed, use power rule and then chain rule, which would yield this derivative. Let's go ahead and do this one next. The derivative of x times y squared. Notice x times y squared. That means I have to use a product rule because I have a product. So let's go ahead and take the derivative of x times y squared. So the way I teach product rule in my calculus classes, I tell students always take the derivative of the first term. So the derivative of x is 1. Keep the second. Next, keep the first term. And then take the derivative of the second, which is y squared. Let's go ahead and do that on the side here. This is the part that students get. This is the part that students mess up the most. So the derivative of y squared is 2y, like the chain rule. I'm sorry, like the power rule. But then applying chain rule, the derivative of y is dy dx. So this would be 2y dy dx. Here are some guidelines for implicit differentiation that you need to follow, because now we're going to get down to the AP style questions. These questions here are AP style. Okay, so these are the type of questions that you're going to see on an exam, whether it's multiple choice or free response. So let's take a look at the guidelines. So the guidelines for implicit differentiation. Step 1, differentiate both sides of the equation with respect to x. So let's go ahead and do step 1 in this problem. So I'm going to go ahead and take the derivative of this relation, this curve, with respect to x. That means taking the derivative of each term. Now what I'm doing here is not distribution, so don't think that, oh, you just distribute the derivative. That's not the way to do it, but I'm taking the derivative of each term. So taking the derivative of x times y will give you 1 times y. So derivative of the first term, keep the second, plus plus the first term, keep the first term. Now take the derivative of y, and that gives you dy dx. Now take the derivative of a positive 3y, that gives you positive 3 dy dx. Take the derivative of negative 5x squared. Well, that's going to be a normal derivative because I'm taking the derivative with respect to x, and that will be 10x equals. This is the part that students mess up the most. They always just drop down the 10. You're taking the derivative of both sides. So the derivative of 10 would produce it will give you a 0. Step 1, check. Now, step 2, collect all the terms involving dy dx on the left side of the equation and move all the other terms. So these are the terms that do not involve dy dx to the right side of the equation. So to illustrate this, I'm going to highlight my dy dx terms in yellow, and I'll go ahead and highlight the non-dy dx terms in green. So I'm going to separate the yellow from the green. And I'm going to stick with the rules here. Left side dy dx, right side non-dy dx. So I'm going to just keep these terms here, but move the other terms by subtracting y and adding 10x to both sides. And that'll give me 10x minus y. And I wrote 10x on purpose in the front as a leading positive term. It's easier for me to read. And I'm going to write these terms as they are. So x dy dx plus 3 dy dx. Step 2, check. I should make these steps here reference steps. So this is step 1. Here's the result for step 1. Here's step 2. Here's the result for step 2. Now, step 3 says factor dy dx out of one side of the equation. This is usually the left side if you follow step 2. So let's go ahead and do this. So I see that I have dy dx here and dy dx here. Let me use a different color. Here and here. That means I have a common factor. So I'm going to go ahead and factor out dy dx. And when I factor out dy dx, well, what remains on this left side of the equation? Just the x plus 3. Now, if you're ever confused about factoring, one way to verify that you factored out correctly is to distribute dy dx to both terms, and you should get the same thing back. So this is now step 3. Okay, so step 3, I factored and I got this result. Check. Final step, step 4, you solve dy dx. This is usually by dividing the factor being multiplied by dy dx. So this is the factor, and this is dy dx, also a factor, but we're solving for dy dx, so that means I need to divide out the x plus 3 to both sides. So my final answer, and this is step 4. Step 4 usually gives you your final answer. Dy dx, dy dx is equal to 10x minus y all over x plus 3. These 4 steps, you follow the 4 steps, you can pretty much solve any implicit differentiation problem, any part A of the implicit differentiation problem, the free response surely. And now let me go ahead and show you B. So here's an AP style question. Part B says evaluate the derivative at the point 2, 6. Let's go ahead and rewrite the derivative. The derivative should be the answer in part A. Now I'm going to go ahead and evaluate the derivative. So plug in x equals 2, plug in y equals 6. So for every x is now a 2, and for every y we have a 6. Now use arithmetic to go ahead and solve, well, not solve, to evaluate the derivative at the given point. 20 minus 6 all over 2 plus 3, 14 over 5. Hopefully my math is correct. 14 over 5 is equal to the derivative. What does that mean? dy dx? dy dx means derivative. Derivative means your slope. I'm going to use algebra 2 notation. This is your m. If you had to find the tangent line, which we are in part C, write the equation of the tangent line to the curve at the point 2, 6. So recall that tangent line is in the form, or the linear form that you want to respond in is the point slope formula, because I could just get the points from here. This is x1, y1, and just place every point in its spot. The m is the answer from part B. Oops, this part right here. 14/5, x minus 2. And you don't want to proceed after this. You leave it alone. Answer in part C is done. Now, should you come across a multiple choice problem, you may have to solve for y. That may not always be the case, but just adding 6 to both sides and then carefully distributing the term and summing up the terms after that. Last problem. So find dy dx given cosine x times sine y is equal to square root of 3/4. I'm going to follow the same 4 steps above. Step number 1. Okay. Look at the top of the page. Step number 1 says differentiate both sides of the equation with respect to x. So let me just write what that looks like. Okay, step 1, if I differentiate both sides of x, I have to use a product rule here. I'm going to do this quickly because this video is already going on 22 minutes. So I always tell students to take the derivative of the first term, keep the second, plus keep the first term, derivative of the second. Now this is the part that gets students all the time. They just took the derivative of a y term. So anytime you take the derivative of a y term, you take the derivative, you apply chain rule, pretend that cosine has something in the inside that's not a simple x. You take the derivative of the inside and you multiply it to the outside. Now take the derivative of the right side of the equation. Square root of 3/4 is 0. Step 2, we're going to go ahead and just separate the terms. All my dy dx terms on one side and all my non-dy dx terms on the other. So this is going to be simple. All I have to do is just add sine x, sine y to both sides of the equation. So I get cosine x, cosine y, dy dx is equal to sine x, sine y. Step 3, not necessary, because step 3 we factor out dy dx. I don't have to factor out dy dx. I already have the factor times dy dx. So simply just going to step 4, dividing out the factor and applying it to the other side of the equation by balancing equations. Those divide out. Step 3 wasn't necessary, so step 4 will always give me my result. Oops. Sine x sine y, cosine x, cosine y. This is totally acceptable. I give full credit for this. However, on the AP exam, and especially in UT Quest and Albert.io, you may have to do some more simplification or rewrite sine over cosine. If the angles match, this is an identity, and that is tangent. Sine over cosine, the angles match, this is an identity, and that is tangent. Y.